All right, so recently we've been talking about logarithms, and we are going to be graphing them today. But we're going to be approaching this just slightly different than we have before, so you can kind of see a little bit more of where these kind of come from. Because understanding that, remember logarithms, hold on, let's start with this. Since the function family name is logarithm, okay, our parent equation is going to be f of x is equal to, right, log, and instead of base 10, we're actually going to do, our standard logarithm, we're actually going to do log base 2 of x, okay? We're going to do log base 2 of x, okay? And understanding that depending on what the base is, this entire thing can change. If all I do is change the base, right, this entire graph is going to look very, very different. So we're just going to start with log base 2, because remember, if I do like base 1, for example, right, nothing really happens, okay? It's not really possible. And I'll show you what that means and show you how that works in just a second, okay? So, but instead of graphing just logarithms, instead of doing our normal table of values, right, because we would need to do a bunch of scientific calculations and stuff like that. Remember that if f of x is equal to b to the x, then f inverse of x is equal to log base b of x, okay? So they are inverses, okay? They are inverse functions. Okay? Meaning that if they're inverses, that's how we're actually going to start graphing this. So I'm going to graph log base b of x. I'm going to graph it in blue. Okay, but remember, since we're graphing, our base is 2, right, in this case, we're going to be graphing f of x is equal to 2 to the x. So we're going to graph our exponential first. Okay? So if you remember, our exponential, it crosses over here at 1. Okay? And then I know it goes down here, and it's asymptotic to the x-axis. Okay? And then it would be 2 to the first would be 2. 2 to the second would be 4. 2 to the third would be 8. And 2 to the fourth would be 16, which we can't even get up there. So this would be our graph. So again, some key points that we're going to utilize in this is our very first point, which is 0, 1. Our second point, which is 1, 1. Sorry, 1, 2, I apologize. 1, 2. Our third point, which is 3. Sorry. My goodness, Mr. Kiefer cannot talk. It would be 2, 4, and then 3, 8. Okay? So remember that when I do inverses, right, it's the same thing as reflecting along let's see if it matches up if I do 45. It's the same thing as reflecting along the line y equals x. All right, so I'm going to go ahead and graph that line. Come on, go. This is our line y equals x. And so in order for me to reflect it, okay, I'm going to take each xy coordinate and I'm going to turn it into what? Xy goes, if I'm reflecting about the line y equals x, xy goes to what? Come on, guys. This is a little review of inverses.
Yx.
Yx, perfect. Okay, so all I'm going to do, right, in order to graph logarithm, in order to graph the logarithm now, all I'm going to do is I'm going to transpose x and y. Okay, so for each of these coordinates, so if I'm going 0, 1, right? My first point should be where? 1, 0. Perfect. Okay, should be over here at 1, 0. Now, if I'm going 1, 2, my next point should be. Oh shoot! That's gonna cover it up. First point should be 1, 0. My next point should be 1, 2, 1. And then it should be 4, 2. I am just jumbling this up. Hang on. Should be 2, 1. Then 4, 2. And then we're going to go 8, 3. Okay? And so now we can kind of start to see what this graph looks like a little bit. So it's going to kind of come up here like this. And go all the way like that. So in the original, or in b to the in the original function f of x equals b to the x, or 2 to the x, right? We notice that it's asymptotic to x equals 0. Okay? Sorry, y equals 0. Okay. So which do you think this thing's going to be asymptotic to the y-axis? Absolutely. Okay? So now instead of being asymptotic to the x-axis, it's going to be asymptotic to the y-axis. Okay? And so this is our graph of log base 2 to the x. Okay? And so we just kind of graphed it like we did in inverse. And it was a lot easier than sitting there and try to calculate, because again, if we tried to make like a table of values, right? If x is 0, this is the same thing as log base 2 of 0, which is what? 2 to what power will give me 0? Nothing. Then if I go 1, log base 2 of 1 would give me 1. Or sorry, 0. Then if I do 2, all right, it gets a little bit easier. Log base 2 of 2 is equal to 1. If I do 3, log base 2 of 3 is what? Right, and that's kind of where it becomes a little bit more awkward. Log base 2 of, 3 is not something we can necessarily calculate. So it'd be harder for us to kind of see how far out this goes. Okay? Okay. So, and that's why we kind of want to use, plus also if I try to do negative, for instance, we're going to notice that there's no way for us to ever do log of a negative number. It's just not possible. Okay? So that's why we graphed this using it as an inverse. Okay? So again, and as far as verbal description, you guys can write however you want to about this. I might write something like like where the asymptotes are. I might write something of like where the like that this is an inverse of b to the x, so on and so forth. Okay? All right, so now let's look at defining characteristics. Okay? What's the domain of this guy? Remember, we're looking at the red. What's the domain of the red? Is it all real numbers? No, because I can't put any negative values in here. So realistically, our graph doesn't even start till 0, but even 0 is not even possible, right? So I know I can get really small to it, but I can't actually equal 0. Okay, so it's going to be from 0 all the way up to positive infinity. Okay? And again, it's a parentheses because I can't actually equal 0. What about range? Our range is going to be all real numbers. It's going to be from negative infinity to positive infinity. And kind of remember that from, again, since they're inverses, come on, where'd my thing go? Since they're inverses, the domain of this one was negative infinity to positive infinity, but the range was 0 to positive infinity. So remember, when they're inverses, all that stuff switches. Okay? Increasing on, well, it's always increasing, so it's increasing along the whole domain. So from 0 to positive infinity. And remember, to tell if it's increasing, I go left to right and see what's happening to my y values. Are they going up or are they going down? And I also want to look at my slopes. Is my slope positive as I'm moving left to right, or is it negative? Okay. Decreasing on. Does this thing ever decrease? Nope. Horizontal asymptotes. Does it have any horizontal, right? The ones that go this way. Does it have any horizontal asymptotes? No. Does it have a vertical asymptote? Vertical asymptote. Does that work? Yes, it does. Where? The y-axis, or the line x is equal to 0, or the y-axis. Okay. All right, what's its x-intercept? That might be a lot harder to solve for later. Right? That's why we introduced this as an inverse, because actually solving for that is not something we're ready to do. But looking at the points that I used, we can see that we do have an x-intercept at 1, 0, or x is equal to 1. So does it have a y-intercept? No. Right? It does not have a y-intercept because the y-axis is my asymptote, which means it never actually touches it. Okay? Maximum value, none. Minimum value, none. Is this bad boy 1 to 1? It has to be. It has an inverse. Remember, that's what makes it an inverse if it's 1 to 1. So it's absolutely 1 to 1. And again, you can always check that as well. Right? So remember, vertical line test tells me, yep, this guy's a function, right? Because my graph only touches the ruler in one spot. In order to determine if it's 1 to 1, I use the horizontal line test, and I go from bottom to top, and it touches the graph in exactly one spot. Okay? So this is 1 to 1. Slope, definitely nonlinear. Vertex, none. Axis of symmetry, none. So it's very simple as far as the defining characteristics for the base one. Okay? All right, but now we're going to kind of look at the transformations. And the formula for transformations is going to look a lot different. Okay? Or actually not that much different. It's going to look very similar to the exponential one. Okay? So right here, right, so at the very top, right, that's my actual transformation formula. Okay? A is going to be amplitude, right, or it's going to be my vertical stretch compression. Okay? Yeah, vertical stretch compression. H is going to be my horizontal shift, left and right. K is going to be my vertical shift, up or down. But then B is going to be my horizontal stretch of compression, or really it's actually going to be my base. Okay? So if we look at this function, right? If we look at the values that we have here, this black one, this is my parent function. Okay? Log base 2 of x, that's my parent function. If you notice that we don't have, the red is supposed to be my transformation. If we notice we just have some weird line that goes along the x-axis. And the reason that is because even though my base is 3 over here, right? Even though my base is 3, right? All of my other values are 0. Okay? So let's make A 1, because that's going to be the standard. Okay? Now we can see, all right, that increasing the base, okay, much like with exponentials when I increase the base, you'll notice that the x-intercept isn't going to change, right? X-intercept isn't going to change, but the base is going to play a big role on if this thing's being stretched or compressed. And then notice that we have a flip. Right? Just like we had exponential growth or decay, if I turn this guy sideways, right? Remember, since they're inverses, if I turn this guy essentially 90 degrees, you'll see kind of what I mean. Okay? So let's go back up here to 2. So let's go to, this is our parent function, essentially. Now if I move h to the left or right, now our graph starts to shift. If I move k up or down, my k starts to move up or down. Okay? But again, my x-intercept doesn't change unless my h or k does. But if my base, no matter what, if all I change is my base, my x-intercept stays the same, and that x-intercept is always going to be wherever A is. Okay? So if I move A, oh, sorry. Oops, no, it's not. It's always going to be, sorry, that is incorrect. It doesn't work quite the same way as it does with exponentials as far as that's concerned. I apologize. Okay. But again, part of the reason why it's always going to intercept at 1, 0, right, is because if you think about my x value, or sorry, my input is 1, log base anything of 1, so we're thinking b to some power equals 1, right? It'll always be 0. So no matter what I change my base to, if my input's 1, my output's going to be 0. Okay? And again, I posted this on Canvas if you'd like to look at it and play around with it a little bit more. But let's go kind of more towards actually practicing graphing. Okay. And I know there's 2 pages to this, and I do apologize. We're actually not going to even do the second page. I mean, you can do them if you want to, but we're not going to do them. Okay? A for the sake of time, and B just because. Okay. So up here at the top, and again, part of the reason that I want you to have this is instead of me going ahead and writing it out like I normally do, this is basically a summary of what the transformations look like. Okay? Now, the difference between this one is it uses the parent graph b to the x, okay? But remember, right, each different b changes what my graph looks like, okay? All right. So, again, this is just kind of a summary. So if I wanted to match, for example, number 1, 1, 2, and 3, I wanted to match each of these functions, okay? I have log base 2 of x, log base 5 of x, and log base 1/3 of x. Okay? So here's what I want you to do. So we're going to do a little sign language today. If somebody can help me remember. Okay? So if you think that number 1 belongs with A, you're going to hold up fist for A with the real thumb on the outside. Okay? If it's B, if you think it's B, it's this, right? Yeah, you're going to hold up all 4 fingers with your thumb in the front, and that's B. And if you think it's C, you just make a little C with your hand. Okay? I think E is, that's D. That's D, B. I believe so. What? I can't remember. Okay? All right, so again, if you think it's A, show me A. If you think it's B, show me B. If you think it's C, show me C. So I'm going to give you guys about a second or two, or like 10 seconds. Look at the graphs, kind of compare them, and which one of them do you think belongs to log base 2 of x? Is it A, B, or C? Which one do you think belongs? Is it A, B, or C? All right. On the count of 3, I want you guys to show me on your hands which ones you think they are. Okay? So, number 1. Is it A, B, or C? Show me. Number 1. Does it match with A, B, or C? See lots of C's. You're all saying C. The answer is B. The answer is B. Okay? And the reason why, if I look at these points, this is 1, 0, right? This point right here is 2, 1. Right? And then this next point over here is 4, 2. And those are the exact same ones from the parent function that we just did. Okay? So this one is log base 2 of x. Okay. What about number 2? Okay? Number 2. Does it belong to A or C? Look at them carefully. A or C? Show me. Which one does it belong to? A or C? All right. It belongs to C. Okay? And again, kind of looking at why. Yes, this point is still 1, 0. Okay? But then if I look at the next kind of point that I can, right, which is this one right here, this is 1, 2, 3, 4, 5, 1. Right? And remember, right, this point right here passes through the points 1, 0, and B1. Okay? And again, that's because, okay? So if I think about log base B of x is equal to 1, okay? This is the same thing as b to the 1 power is equal to x. Sorry, I put b to the 1 power is equal to x. Right? So if my x, or so if my y, sorry, if my x then, right, my x was 5 here, this is the same thing as 5 to the first is equal to x, which means x is 5, okay? Or another way to think, sorry, b to the first is equal to x, sorry, and if we know that x is 5 in this case, it means b to the first is equal to 5, which means 5 is equal to 5. So b has got to be equal to 5 in this case. Okay. All right. So this belongs to log base 5 of x, which means that this one, sorry, which one do I use this one? This one is log base 1/3 of x. Okay, and again, the reason why, point that we still have in common is over here at 1, 0. Okay, but if I look at the next point, okay, next point is 3, 1, or 3, negative 1. Okay, the only way that I can get a negative for my output, right, is because remember, 3 to the negative first is the same thing as 1/3. Okay. Remember, negative exponents, right, produce fractions. So the only way that this thing, our graph, can ever go down negative is if my base is a fraction. Okay? Here we go. So for number 4, 5, and 6, we're going to state the domain, or we're going to graph each function. We're going to state the domain and range, identify the parent function, and describe the transformations. Now we're not going to have to do the identify the parent function, right? Because if I look at log base 3 of x, log base 3 of x plus 2, negative log base 3 of x minus 1, right, my parent function for all three of these, right, is log base 3 of x, okay? Now, as far as describing the transformations, we're going to kind of look at that in just a second. So the first thing I want to do is I want to graph log base 3 of x, okay? So again, I know guaranteed it's going to pass through this point. And then the other point that it's going to pass through is going to be, so remember, it's going to pass through 1, 0 every time and b, 1 every time. And b, in this case, is 3. So the point it's going to pass is 3, 1. 1, 2, 3, 1. Okay. And I'm just going to go ahead and graph my curve. As far as transfer domain, my domain is still going to be from 0 to positive infinity, because it's only my positive x values, not including 0, because I still do have my asymptote here on the y-axis. Okay. My range, all real numbers, so negative infinity to positive infinity. And then describe the transformation. Describe the transformation. This is the parent function. Function, no transformations. Okay. Now let's look at number 5. Okay. So number 5, what I'm going to have to do here is I'm going to have to look at the transformations first. Okay. So for x plus 2, right, remember that my transformations, right, f of x is equal to a times log base b of x minus h plus k. Okay. So looking at this, right, we have h, which is equal to negative 2, meaning that we're going to take the parent function and we're going to shift it left 2 units. So shift parent function. What the heck? The heck just happened? Function left 2 units. Okay? And there's no other transformation, right? So I'm going to take this function right here. Here's my parent function. I'm going to take each of these points, I'm going to move them left 2 units. Okay? And since this is the y-axis, I'm going to move that 2 units. I'm going to take every single point, I'm going to move them 2 units. Okay? Which gives us here, here, right? And then I'm just going to, and again, now my asymptote, which was over here at the y-axis, is now going to be over here at negative 2. And so my graph then becomes this guy. which is the parent function, just shifted over 2 units. All right. My domain now is a little bit different. My domain is actually -2 to positive infinity. My range is still all values. Okay. Now we're going to look at number 6. What? Okay. Number 6. I don't know what just happened there. Right? So keep in mind that this -1 here is actually my k value. So if you don't see it in parentheses, it's not included in the logarithm. Okay? So for this, again, applying this, our a is -1, which means we have a reflection across which axis? Remember, when a is negative, we have a reflection across the x-axis, y-axis, which one? X-axis. Okay. Now, the other values we know is k is equal to -1, which means we shift down 1 unit. Okay? So I'm going to take that parent function, and I'll use, I'm going to do, so 1, 3, 1. This is my parent function. Okay. I'm going to reflect first. So I'm going to reflect across the x-axis. And so now this point that was over here at 3, 1 is now going to go down here. And so I've reflected. Okay. And now I'm going to move all of them down 1 unit. So this point here is going to go down 1 unit. This point here is going to go down 1 unit. Okay? And so that's going to give me this point and this point. Why does it keep doing that? This point and this point. But again, I didn't shift left or right, so even though I reflected, my axis is still going to be my graph. Okay. There you go. Now you're probably thinking, well, that negative in front, that made it reflect across the x-axis, but so did having a fractional exponent, a fraction for my base. Right? So which one really does it? The truth is they both do it. Okay? And again, part of that reason why is negative log base 3 of x is the same thing, again, remember our rules, of log base 3 of x to the -1st power. Okay, you're applying our properties, which is the same thing as log base 3 of 1/3. So we do have fractional exponents in here. Okay? And all different types of property. 1 over x, sorry. 1 over x. Okay? So it's essentially the same exact ideas. Okay? Now for domain and range, they're actually not going to change at all. My domain is still from 0 to positive infinity, and my range is from -infinity to positive infinity. All right. Any questions on this? No? Okay, I'm going to go ahead and stop recording. I will be posting this, the video, as well as this completed one momentarily. But please go ahead and you may now start your assignment for the day.